If we go up and look at the effects of hyperpolarization, we're going to see effects that are pretty similar to hypokalemia, again, kind of in the opposite direction. First of all, we're going to have difficulty repolarizing the cell. It's going to lead to prolonged depolarization or hyperexcitability. Since in all excitable cells, repolarization is dependent on potassium leaving a cell, that means the extra potassium outside the cell is going to make it hard for potassium to leave when we're trying to repolarize the cell. That leads to hyperexcitability, and in the CNS, that can lead to a lot of different functions. A primary one would probably be restlessness and overexcitability. In the heart, that's going to lead to a slower heart rate. It's going to slow down heart conduction. That's going to have its own consequences. Like you can slow down enough to get ectopic pacemakers. It's going to slow down contractility. And we can see it on an EKG as a wide QRS because it takes longer to repolarize that cell. In fact, it can get so wide, or we can delay out that repolarization so long that we can get ectopic pacemakers because a cell is still depolarized when another cell comes out of the refractory period, and it'll be activated by its neighbor then, leading to another pacemaker or an ectopic pacemaker. Looking at muscle, we're actually going to get overexcitability of muscle, which can lead to cramping, and if it's continually cramping, it's going to become weak. The other issue is because those muscles are dependent on mobility of the GI tract, too much excitability, too much muscle can lead to pushing through the contents of the GI tract too fast, causing diarrhea. Note then that this is going to lead to acidosis because we're not going to be able to pick up the bicarbonate. If we can't pick up the bicarbonate, we've got acidosis, and acidosis is going to increase the hyperkalemia. Now, when we look at ion imbalances, when we look at potassium imbalances compared to other mechanisms, one of the first things that's probably pretty obvious is there's less control of potassium. That might be one of the major reasons why potassium imbalances can often lead to death. We don't have nearly as many control mechanisms as we did for sodium. For the most part, hyperkalemia can be corrected by a slight increase in absorption in the proximal convoluted tubule. Also, the DCT and collecting duct can decrease the potassium secretion so the potassium levels are maintained or increased. It's going to be further stimulated by low potassium and even acidosis. And the acidosis is important because normally in acidosis we'd expect more potassium outside the cell. We'd actually want to decrease that excretion of potassium. So in case the acidosis is reversed, we have that potassium available to get back inside of the cells. One of the ways that this probably works is the same kind of exchange of potassium and hydrogen exchanges across the tubular membrane in the proximal convoluted tubule. So again, if there's more acid going over into the filtrate, there's more potassium coming back into the blood, decreasing the potassium excretion. Potassium levels are too high. The DCT can increase excretion of potassium. It does this in response to excess extracellular potassium. Aldosterone can stimulate it. Again, aldosterone causes a reuptake of sodium at the expense of potassium. So bringing sodium in from the filtrate pushes potassium back into the filtrate, and that's going to increase the excretion by the distal convoluted tubule. Another thing that can increase excretion is a high GFR. Now, this is actually a pretty important mechanism because it balances and isolates potassium effects from sodium effects. And what I mean by that is if sodium goes high, that's actually going to increase GFR because we have more sodium around, more fluid around to go through the kidneys. And that would increase excretion by the distal convoluted tubule. But that high sodium is also going to decrease the presence of aldosterone as the body tries to get rid of that sodium. And the decreased aldosterone is going to inhibit the excretion of potassium. So potassium is fairly well isolated from sodium swings because high sodium increases GFR, which increases potassium excretion, but high sodium decreases aldosterone, and since aldosterone increases secretion, the decreased aldosterone with increased sodium causes actually a decrease in potassium secretion, so these two balance out. Now, because there's so few regulatory methods in the body that has to deal with potassium imbalances, any large increase in potassium due to cellular release likely can only really be cured by renal dialysis. Thank you.